Hi rabbits, Research Turtle here. Today we are unlocking one of the most fascinating concepts in modern physics, time crystals. It sounds like science fiction, but as we'll see, it's a very real new phase of matter that breaks the symmetry of time itself. Let's start with something familiar. Nature hates monotony. In space, atoms break symmetry to form crystals, like ice or diamonds. This is spatial symmetry breaking. The atoms arrange themselves in a repeating pattern in space. So, the Nobel laureate Frank Wilczek asked a crazy question in 2012. If matter can repeat in space, can it also repeat in time? Can a system have a heartbeat even in its lowest energy state? At first, the answer was a hard no. Thermodynamics seemed to forbid it. Why? Because a system moving in its ground state looks suspiciously like a perpetual motion machine. If a system is in equilibrium, its lowest energy state, it should be stationary. Motion requires energy exchange. So, for a while, time crystals were considered impossible. In fact, in 2014, a no-rho theorem was proven by Watanabe and Oshikawa. They mathematically confirmed that time crystals cannot exist in thermal equilibrium. But that wasn't the end. It was a pivot point. Physicists realized that to make a time crystal, we have to break the rules of equilibrium. We need a system that is constantly driven by an external force, but, and this is the key, never heats up. So how do we cheat heat? We need three ingredients. First, a many-body system of particles. Second, a drive. We use a floquet system, which means we periodically shake the system, like hitting it with a laser pulse. And third, the trap. We introduce disorder to create something called many-body localization, or MBL. This prevents energy from spreading and heating the system up. It locks the energy in place. Here is the smoking gun signature of a time crystal, period doubling. Imagine pushing a child on a swing. Usually, if you push once every second, the swing moves once every second. But in a time crystal, if you poke it with a laser pulse every 1 second, t, the material responds every 2 seconds, 2t. It creates its own internal timeline, breaking the symmetry of the driver. It essentially says, I will march to my own beat. But isn't that just a clock? No, a normal clock will drift if the mechanism is imperfect. A time crystal has rigidity. Even if your laser pulse is a bit noisy or the timing is slightly off, the time crystal locks firmly into that 2t cycle. This stiffness against chaos proves it is a true, distinct phase of matter. In 2017, theory became reality. Two independent teams found that signature. One team at the University of Maryland used trapped ions, and another team at Harvard used impurities in a diamond. Both observed that signature oscillation. It proved that time crystals weren't just math, they were real physical systems. Then, in 2021, we hit the gold standard. Google Quantum AI used their Sycamore processor to simulate a time crystal, using 20 qubits. Because they could program the disorder perfectly, they created a true MBL time crystal that lasted for hundreds of cycles, without decaying. It was a definitive victory over thermodynamics. Fast forward to today, around 2026, we are moving from delicate quantum chips to the macroscopic world. Aalto University has created time crystals in superfluids interacting with mechanical devices. Meanwhile, researchers at Kew Boulder have managed to create them at room temperature using liquid crystals. We are moving from the lab bench to robust devices. So what does this matter? What's the killer app? The first is quantum memory. Quantum computers are forgetful. Their qubits lose information easily due to noise. Because time crystals are stable in time, they can protect quantum information, drastically reducing the cost of error correction. The second is the perfect tick. Because they are so rigid against environmental noise, time crystals can act as ultra-stable references for the next generation of atomic clocks. This could enable navigation systems that don't even need GPS, perfect for deep space travel or autonomous driving in tunnels. Finally, sensing. Because time crystals exist on the edge of a phase transition, they are hypersensitive to things like magnetic fields and gravity. Future bioqubits could use this mechanism to monitor live cells, or physicists could use it to hunt for dark matter. It has been a decade of revolution. We went from "physics forbids this" in 2014 to "here is the proof" in 2017 and 2021 to "how do we engineer this today?" It is one of the fastest transitions from theoretical impossibility to practical engineering in history. In conclusion, the age of time crystals has begun. Time is no longer just a background screen where events happen. It is a dimension we can now structure, order, and engineer. We are literally crystallizing the future. That's it for today. Turtle out.